Hello everyone, welcome to the OneClass channel. My name is Millen, and I'm a software engineering student at Carleton University in Ottawa, Canada. Today, I will be going over some commonly asked physics questions at both the high school and university or college levels. If you're interested in getting help with your homework, or if you're interested in getting some tutoring, check out the links in the description below. Cool, so we got a fun time full of physics ahead of us. I'm going to switch my screen ASAP fast. And we can get this physics experience started. Okay? Cool. So, let's take a look at the first question that we got on the menu today. And it is presenting the following situation, okay? So it looks like we have a person that's asking us, please correct me, what did I do wrong in this quiz? My teacher only gave me a grade but didn't mark what was right or wrong. And, we should basically just trying to correct this, okay? So if we zoom into the page a little bit here, let's see if I can actually bring this over. Even better, okay? So we have the actual picture just ready for action here. So we're presented with the following situation. Okay, so we are given uniform acceleration. Okay, so I'm gonna just take note of that. Star uniform acceleration. That means our acceleration never changing, which is pretty important because that's going to allow us to use kinematic equation, kinematics equations. Now, kinematics equations are awesome because they, they're fairly simple to use, and they can always tell us the right answer of the things that we need for constant acceleration. But as soon as that acceleration changes, we're kind of out of luck, and we can't use our kinematics anymore. But we're not going to worry about that right now, okay? So, given uniform acceleration, an object has an initial velocity of 15 meters per second towards the east. And after 20 seconds, it has a velocity of 40 meters per second to the west. Thinking to our compass, we know that our compass is looks a little bit something like this. Never eat shredded wheat. A great way to remember it. So initially, our velocity, let's call that u for initial velocity. That's pretty common. Sometimes you might also see it as like vi for initial velocity. So our initial velocity is 15 meters per second towards the east. East. So going from left towards right, if we're looking at a compass, and our final velocity after 20 seconds, okay, that's another thing that we're going to need to keep in mind. Our time here, 20 seconds. And after 20 seconds, it has a final velocity of 40 meters per second west, going the complete opposite direction. So for final velocity, it's fairly common for people to use v, and we got to put an arrow on top of it. Remember, it's a vector, and it's going the opposite direction. So this is 40 meters per second. That's pretty fast. And this is west. It's good to surround it by square brackets just to specify that it's a direction. Okay, so the first question on the menu today, or the first thing it's asking, is the average velocity here. Okay, so keep in mind that our velocity, initially, we're going towards the east, and then over some time, we pretty much made a whole U-turn and, switched our directions. Okay, so the first thing that we're going to need to do is we want to define a direction. Okay, it seems that you've done your math well for the person asking this, but I'm going to write on top of you just to show like why it's completely right and why you are a physics rock star. Okay, so define a direction. Let's say east is positive. That would mean that west has to be negative. There's nothing wrong about going towards the west. It's just like how we have to set up our things. Okay, so our u, another way that we can write our u is towards the east, so that's going to be positive 15. And our v, since it's going towards the west, is going to be negative. Okay, so I'm just putting these signs here. Now to find the average velocity, Our average velocity is the sum of our velocities, because we have constant acceleration, uniform acceleration. So that means we just add the initial velocity plus the final velocity and divide it by the time. Oh, not by the time, that would be the acceleration. We're going to divide it by 2. And this is average velocity. Okay, so that's exactly what we're going to do. So our initial velocity is 15, positive 15, because remember, towards the east, we said is going to be positive. So plus 15 meters per second, plus the final velocity. Now we know our final velocity is going to be a negative number because we're going towards the west, and we said towards the east is positive. So we got to do negative 40 meters per second and divide that whole thing by 2. Okay, so I know that's going to be 25 over 2, negative 25 over 2. That negative is extremely important. Meters per second over 2, and that translates to negative 12.5 meters per second. And it might be even better to even write that this is towards west. Okay, so this is our average velocity, and that makes sense because our final is going faster west than we were initially going east, so our average should be towards the west. Okay, so yeah, that's cool. So under here we had negative 25 over 2. It's just better to write that as like an actual, or to calculate that through to negative 12.5. Okay, awesome. So the next part of the question is asking, what's the change in velocity? So the change in velocity, as is written here, is simply is represented by delta V. The delta is the triangle looking thing to the left side of the V. That's a Greek letter to specify final minus initial. This is not just for velocities, but for distance as well, for time. This will always, that delta operator, it means difference, final minus initial. Don't forget it. Keep that in the brain forever. You're gonna need it forever. Okay, so we're gonna do the change of velocity is like well, that's just our final velocity minus our initial velocity. So we used v and u, so we're gonna continue to use that convention here, v minus u, both as vectors, but we're gonna convert them to follow our same east-west positive minus convention. So our final velocity is towards the west. We said west is negative, so that's got to be negative 40 meters per second. And then we're going to minus our initial. Our initial was 15 meters per second towards the east. We know our east is the positive direction, so we're going to subtract a positive number from here. Plus 15 meters per second. And, well, compute that math. 40 minus 15, or negative 40 minus 15, negative 55 meters per second, which is precisely what you got here. So a big high five on that. Good job. Negative 55 meters per second. Awesome. Cool. Okay, so that addresses the second part of the question. Now we can move on to the third part of the question, the acceleration. Now the acceleration is, by definition, acceleration is the change in velocity with respect to time. How much does your velocity change over time? That's what acceleration defines. And we know that the acceleration is constant. That was like one of the first little clauses of this situation that was presented to us. So to calculate the acceleration, we need to find our change in velocity divided by our change in time. That's the definition of acceleration. And acceleration is a vector. Do not forget that acceleration is a vector. If you forget that, you're going to be in trouble. Big trouble. Okay, so it's going to be the change in velocity divided by the change in time. We know that our change in velocity, well, we just calculated that in our previous question. That's negative 55 meters per second. That's where it came from. And divided by our time, how long did it take for us to change from our initial velocity to our final velocity? The question told us 20 seconds. Okay, so we're going to divide that by 20 seconds. And if you look at the unit, The unit is going to be meters per second, which is equivalent as saying meters per second squared. Let me just erase that. So meters per second squared. Essentially what that means is our meters per second changes every second by this amount. Okay, so then we're going to do a quick calculation. 55 divided by 20. Now, I am not the sharpest tool in the shed, so I can't do that in the mind instantly, but that's okay. That's why we got calculators. And I got negative 2.75. Meters per second squared. And negative, well, that for the same reason we have going towards the west as our negative direction. So even better, it would be to say like the acceleration as a vector is 2.75 meters per second squared in towards the west. Okay, that would be the vector way of saying this. And for this as well, we want to specify that this is going west. Okay, if like the question asker was mentioning that the teacher gave a mark but didn't say was right or wrong. If there were things wrong about this, I think what could have went wrong is that the directions of the vectors maybe were not specified extremely clearly. Also, you want to convert your answers into like decimals. In general, decimals are generally preferred as a final answer in physics. Math is a little bit of a different story, but in physics, you're gonna, and especially engineering, because that's physics and engineering are tightly related, like siblings. You're gonna want decimal type answers. Okay, and yeah, so now we can move on to the last little section of this question, which is asking us for the displacement. Basically, how much did we move? What distance did we cover for this to be possible, for us to change our velocity from 15 west to go to 15 east to go to 40 west, all the meters per second. Okay, so for this, definitely from what we got here, it's a great start. We want to start with our kinematics equations. Okay, so the kinematic equation that we want to keep in mind here is that our change in position, our x, or our delta x, which is displacement, we could also write this as d, is equal to our initial velocity times time. Whoops, not that one. So our u t, and we will add plus 1/2 at squared to that. Squared. Okay, so this comes from kinematics. Kinematics equation. Okay, so to solve for d, well, d is already isolated, so we just have to sub in our numbers, and then we can be very happy that we found the displacement. Okay, so d is going to be equal to, our u value is positive 15. We're going to still follow our east-west, east positive, west negative convention. So our u is positive 15 meters per second, multiplied by our time, that's 20 seconds, plus 1/2 multiplied by our acceleration. In the previous question, we calculated it to be negative. That's very important. It's negative. Negative 2.75 meters per second squared, multiplied by t squared. And t is 20 seconds, but we got to square that. Okay, so 20 times 20, 400. Okay, now I'm going to send this all through my calculator to figure out what the numerical answer to this calculation is. 15 times 20 plus 0.5, that's the same as divided by 2, times negative 2.75 times 20 squared. And my result for this is d is equal to negative 250 meters essentially what this means is our final displacement is 250 meters west of where we started from. Okay, so if we started here, we were going like this, and then eventually our acceleration took over, and this is our end point right here. Okay, kind of like we made a little U-turn, and that is our position. And we calculated the same thing here. That's awesome. Or numerically, that's awesome, but we're looking for vectors here. So to say answers are all correct, yes, but to be held to higher physics standards that are very common, especially with what physics leads to into like engineering as well as more general science, we need to incorporate the vector quantities. Okay, so the above solutions are numerically good. However, the given info is with vectors, so the answers would be better as vectors as well. Note a direction, not a direction, note a direction instead of a sign for these situations. Cool.